Your physics teacher is extremely generous and they take you out go-karting. Of course, on the condition that you complete a physics report on the experience, right? That's fair. So a section of the track is given. So part of it is circular and then another part is straight. So two sections. And the radius of the circular section is given to be 20 meters. So let's just put that in on our diagram. 20 meters. And the combined mass of you and the go-kart is 120 kgs. And now it takes you 5 seconds, rather 5.0 seconds, to complete the half circle section going from A towards B. So you're going in this direction, so clockwise. Part 1, calculate your speed. So we know from level 1, speed is distance over time. However, in this context, our path is circular, and so our distance is actually just half the circumference of the circle formed with the radius of 20 meters. Right, so that's the distance traveled, half of the circumference. And the time is given as 5.0 seconds. So working that out, we recall circumference is 2 times pi times the radius, where we are given the radius. So substituting that in, 2 times pi times 20 meters, or 40 pi. And now that is the full circumference, but since we're just covering a distance of a half circle, our distance would be half of the full circle, giving us 20 pi. And we can, of course, evaluate that on our calculator. 20 shift pi, 62.83 meters. Alright, so that's our distance, and we know, speed is distance over time, which is 20 pi, or 62.83, divided by 5.0, which in this case would give 4 pi. And as a decimal, 4 shift pi, 12.57 meters per second. However, we need to round sensibly, so looking at what we're given, the radius 20 meters only has one significant figure, so if we're being accurate here, we should round our answer to one significant figure as well. But do leave your unrounded answer available for further calculations. So to recap that, we're traveling in a circular path. To work out average speed, we need the distance, which is in this case half of the circumference, divided by the time. So this equation is a good one to remember for circular motion problems, to work out the distance. Alright, part 2. At position A, draw a vector labeled v showing the velocity. Alright. So we know in circular motion, the velocity is tangential to the path. So what I mean by that is at position A, let's just do it on the edge of the circle so we can see it. Our velocity, v, is tangential to the circle, to that circular path. Cool. And the next question, let's actually skip part 3 and jump to part 4. Draw a vector labeled AC to show the direction of the centripetal acceleration. So in circular motion, the acceleration is inwards. So if you look up the etymology, like the origin of the word centripetal, it relates to inwards. So centripetal acceleration is acceleration acting in towards the center of the circle. Cool. And finally, while we're here, looking at part 6, it's asking us to draw a vector labeled FC to show the centripetal force. Well, we know the centripetal force acts in the same direction as the centripetal acceleration. Right? In order to provide that acceleration, the net force must be acting in that direction. Alright, now re-looking at the question. So we've done all of the vector diagrams to show velocity, acceleration, and force. But for acceleration and force, we can also calculate their values. So let's do that. Looking at your formula book, you'll find the equation. Let me just label that 1, 2. The centripetal acceleration is v squared over the radius. And we worked out the speed, right? 12.57 meters per second unrounded. And we're given the radius of 20 meters. So we can compute that. Pro tip, if our last answer was the unrounded value that we're looking for, we can just use shift answer. So it was speed squared divided by radius. So what's that? 7.9 meters per second squared. All right, and again, to one significant figure, that would be 8 meters per second squared. So that's the centripetal acceleration. So on your go-kart, you are accelerating 8 meters per second in towards the center. Right, and that's what's changing the direction of your velocity. And now part, 5? Calculate the centripetal force of the go-kart. So we know centripetal force. In the formula book, you're given mv squared over the radius, and that actually just comes from mass times acceleration, where acceleration is the centripetal acceleration. Right, so we see that acceleration appears there, and then mass. Of course, that's from Newton's second law. F net is mass times acceleration. So to work it out, all we need to do is write out the formula, but acknowledge that v squared over r is 8, and then we multiply that by the mass of 120 kgs. And actually, instead of using 8, we should use our less rounded answer. 120 times answer, 947.5. And again, to one sig fig, that would be 900 newtons. So that's a full analysis of the circular motion going from section A, or position A to position B. We've labeled the velocity, acceleration, and centripetal force. We've worked out the magnitudes of the speed. We did that first, so that we could then work out the magnitude of the centripetal acceleration, and so we could then work out the magnitude of the centripetal force. Now, of course, that's not the whole track. After the circular path, we transition to the straight path and begin to accelerate to the right. Cool. So we're now here, and we see this nice open bit of path, right, the straight, and we put our foot on the pedal all the way down because we want to go fast, so we accelerate. And now at that position, draw a vector labeled v, showing the velocity, as well as a vector labeled a, showing the acceleration. So the question tells us we are accelerating to the right. So let's put our dot. We know we will accelerate to the right. And in fact, our speed is also to the right. All right, so I'll label that v as well. And I'm just putting them very close to each other so we can see them separately. Yeah. Notice how that's different to the circular part of the track, where velocity and acceleration were perpendicular. In the straight part of the track, they are parallel. And that's actually leading us nicely to part C. Compare and contrast the magnitudes and the directions of velocity and acceleration at the two positions. So at position A, what do we know? We know that V is up, A is right. We know the magnitudes as well. Right, we work those out. Thinking ahead, we don't actually know the magnitudes of B, so we can't compare them directly, but what we can do is mention if they're constant or if they're changing. Cool. Let me just set this up. And then there we go, V and A again. So the direction, I'm just setting up a table so we can see everything on one page, and then we can put it into words. So at position A, velocity is up, acceleration is right, for the circular motion. The magnitude of velocity is actually this over here, the speed. So the speed doesn't change, but what does change is the direction of velocity, as we go around the corner. And acceleration is also has a constant magnitude of 8 meters per second squared. Oh. So for magnitude at A, velocity, the magnitude is constant, and acceleration is also constant. Now at B, velocity and acceleration are both to the right. Cool. And now at B, just looking at the question, we aren't given quite enough information, but we know we're accelerating to the right. We could assume it's constant, right? That's a fair assumption. So in level 2 motion problems, acceleration will be constant. So we could write constant, and that is an assumption. I'll let the person know who wrote these questions, happens to be me, to fix that one up. Right, but again, state your assumptions. Now velocity at B, would it be constant or increasing or decreasing? So if we get to this open bit of road and we accelerate harder than we were accelerating in the circular path, our velocity will increase as we have increased our acceleration. So that's what I'm going to assume. And so looking at our table here, at A, we've summarized the directions and magnitudes, and at B, we've also summarized the directions and magnitudes of both velocity and acceleration. Now your task would be to put this into, 4 sentences, right? For each parameter, for each position. All right, and now question D. Unfortunately for you, your physics teacher got the best lap time, as they completed the circular section in only 4.2 seconds. Now, using what we learnt in section A, how could you increase your speed to win next time? Okay, so you want to shave off, at least 0.8 seconds in this circular section. And what will you need to change to do that? So to go faster, going back to part 1, the distance you travel will be the same, right? Assuming you take the same line, right? So let's say you drive down the middle instead of trying to optimize a path, which is what you do in reality, but let's simplify it a bit. So you travel the same distance as your teacher. Okay. So to decrease the time, you will need to increase your speed because they are inversely proportional. So let's write that as our first point. So scrolling down, you travel the same distance. All right, and we worked that out actually. It was 62.83 meters. Okay, so we can't decrease that. Right, in reality you could. That's actually how you would probably get a faster time, but let's assume that distance is fixed. We know that distance and time are related to velocity, and if you want to decrease your time for a fixed distance, you must increase your velocity. So need to increase velocity for a quicker time as distance is constant. Right, and I wrote the equation and I showed that speed or velocity and time are inversely proportional with those arrows. Okay, so how do we increase speed? So going back to our analysis, looking at the centripetal force, Fc equals mv squared over the radius. So what could we change? Could we change the radius? No, right? That's tied to the distance, so that's fixed. We can't change the track. But we can change the mass, perhaps, and we can also change the net force. So let's have a think. So we know Fc is mv squared over r, and let's rearrange for v so that we can clearly see the relationships. So v squared, multiply both sides by the radius, divide both sides by mass, and we can see that v squared is equal to centripetal force times radius divided by mass. And so radius is fixed. We want to increase the speed, so we could either increase the centripetal force or decrease the mass. Right, so let's put that as a sentence. Need to either increase centripetal force or decrease mass as radius is constant. Okay, so that's what we need to do. How are we going to achieve that? So let's think about decreasing mass first. You could use a lighter weight go-kart, right? Or you could use a go-kart that's nearly out of fuel, right? It'll have slightly less mass. You could lose weight, kind of impractical though, especially if you're just wanting to beat your physics teacher. Let's not do that. So that's decreasing the mass. So mass can be decreased by using lightweight go-kart. Alright, so you can blame your equipment in this instance if you had a slow and heavy go-kart. Now, how can we increase the centripetal force? So centripetal force, as you should know, is not a force. It is a net force. So thinking back to the go-kart scenario, what is the force pushing it into the center of the circle? Right, assuming the track is flat, the force pushing it inwards is actually friction. So this centripetal force comes completely from friction. So how can we increase friction? So increasing centripetal force means increasing friction. So we could use grippier tires, right? Different tires with more grip. That would be one way to increase friction. Cool. Not in level 2, but the more, how do I word it? Friction relates to how hard you push down on the ground. So actually increasing mass does increase friction. So there's this extra relationship that we could consider. But for level 2, I'm going to leave it for now at decreasing the mass and increasing the friction by using different tires. Cool, so let's just quickly recap this question because it was a lot. So circular motion, we analyzed a circular section of track to find speed using the circumference and time. We then found centripetal acceleration using that speed. We found centripetal force using that acceleration or speed. We then also labeled clearly a vector diagram showing velocity, acceleration, and centripetal force, both in circular motion and in linear motion. We then compared velocity and acceleration at those two positions in terms of their direction and the magnitude, whether it was constant or changing, right? In this case, it was increasing for velocity. We then considered how we could improve our own lap time. To decrease time, we had to increase speed. To increase speed, we had to increase centripetal force or decrease mass. Alright, that's it. I'm going to go back to the track. See you later.